Hello Noddies, welcome back to the channel. In our previous videos, we learned that an LC circuit can resonate when XL is equal to XC, but resonance has another fascinating property. It can make a voltage appear much larger than the source voltage, and it can make a current appear much larger than the source current. Today we will study two important resonance phenomena, the voltage magnification and the current magnification. We will derive the equations, design the circuits, understand why Kirchhoff's law are still valid, and finally discuss why these circuits are not practical amplifiers. So let's get started. Let's compare both circuits side by side. One on the left is the series RLC circuit and one on the right is the parallel RLC circuit. Both operate at resonance, but they magnify different quantities. The series RLC circuit produces voltage magnification, whereas the parallel RLC circuit produces current magnification. For the voltage magnifier, let's start with the series RLC circuit. So at resonance, XL is equal to XC, therefore the impedance is equal to R and the circuit current becomes I is equal to V in by R. The voltage across the inductor is VL is equal to I times XL, and in order to find the quality factor is the ratio between the effective energy storage element to the energy dissipating element. Here the inductor is the energy storage element and the resistor is the energy dissipating element, and by finding the ratio we can find the Q, where Q is equal to XL by R, or if we are finding it by capacitance then it is 1 by XC into R. Now let's look at the parallel RLC circuit. Here again at resonance the XL is equal to XC and the current to the resistor is given as V by R. Now the current through the inductor becomes IL is equal to V by XL. By comparing this with the source current, we get Q is equal to IL by IS, which is nothing but RP by XL or RP into XC. From this, we can understand that the quality factor directly determines the current magnification and the voltage magnification. Let's now design both circuits using exactly the same specification. Here, the Fn is kept as 27.4 kHz while the L is equal to 1 millihenry and our input is 1 volt and we need the output voltage to be 10 times of the Vin. Similarly, for the current circuit, the Fin is kept as 27.4 kHz and the L is kept as 1 millihenry and the In is equal to 100 milliamps. So we need the current output of 10 times of the input current. So this means that we want 10 times of the voltage magnification and 10 times of the current magnification, which means that the quality factor is equal to 10. Both circuits must resonate at the same frequency. Using the F naught is equal to 1 by 2 pi root of LC formula, we find the capacitance in both the circuits. Now the XL is equal to 2 pi FL, where XL is given as 172.6 ohms, and similarly here the XL is given as 172.6 ohms. By using the quality factor, we can find the resistance. Here the resistance is found to be 18 ohms and here the resistance is found to be 1.8 kilo ohms. Now you may wonder how this works. Does it disobey the KVL? Now let's find the answer. For the voltage magnifier, the current formula is given as I is equal to V by R. Here from this we can see the current and resistance are inversely proportional. So when the resistance gets decreased, the current increase. So a small resistor means a large current. Since it's a series RLC circuit, same current flows through all the components. Here the inductor converts this current into voltage. VL is equal to I times XL. So we obtain a voltage that is much larger than the source voltage. Similarly, for the current magnifier circuit, here V is equal to I times R. So here the large resistor gives us a large voltage and the inductor converts this large voltage into a large current. At this point, we may wonder, if my source is only 1 volt, how can I get 10 volts across the inductor? Are we violating the Kirchhoff voltage law? The answer is no. At resonance, this is the formula that is given by KVL. So from this we can notice at resonance the XL and XC are same here, so that the inductive and capacitive voltages just cancel out each other. Therefore, KVL is perfectly satisfied. We are not creating any new voltage here. We are just converting the current into voltage. The same principle is applied as KCL in the current magnifier circuit. You can try this on your own. So this is our expected graph. For a 1 volt sine wave, we should get a 10 volt sine wave as the output. And this is the expected output for the current magnifier circuit. For an 100 milliamps current input, we should get 1 amps current at the output. So now let's try to simulate this in cadence and verify whether we are getting our output. Open your cadence, press I to go to add instance window. Here find your resistor from the analog library. For voltage magnifier, our resistance is found to be 18 ohms. Press R to rotate your resistor, place your resistor, press I again, go to the add instance window. Here find your inductor. R inductor is found to be 1 millihenry. Press R to rotate your inductor, place an inductor. Press I again. Go to analog library. You'll find your capacitor. Our capacitor is found to be 33 nanofarad. Place your capacitor. Press I again. You'll find your V sign from the analog library. Our input amplitude is set to be 1 volt and our frequency is set to be 27.4 kilohertz. Place your voltage source. Press W to finish wiring your circuit. Press L in your keyboard to label the wires. Here I am labeling the wires as resistor, inductor and capacitor. Place your names respectively. Check and save. This is a circuit. Launch ADL. Here give your trans as 1M. Select your output nodes. I am selecting the resistor, inductor and capacitor. Run your simulations. So this is our output. Here click on the graph and press M to mark the graph and press D again to mark the difference between the graph. So this is our input. Here we can see the sine wave is oscillating from plus 1 volt to the minus 1 volt and this is our output across the capacitor. Here click your graph, press M to mark the graph and press D again to find the difference. Here we can see the output waveform is around 18.6 volts which is near to 20 volts. So for a given 2 volt input we got 20 volt as the output which is our perfect graph and this is the voltage across the inductor which is not 20 volts. We can see why. From this we can see plotting the voltage across the capacitor is straightforward because one terminal is connected to ground. However, for the inductor, neither of the terminal is connected at the ground potential. If I directly probe a node, I won't obtain the actual voltage across the inductor. To measure the true inductor voltage, I need to take the voltage difference between its two terminals. Therefore, I will use the cadence calculator and subtract the voltage of the two nodes connected to the inductor. This gives the actual voltage across the inductor and allows us to correctly observe the voltage magnification effect. Here click your inductor graph, right click on your mouse. Here click send to and click calculator. So since this is a circuit, the inductor value should be subtracted from the inductor node and the capacitor node. So now let's try to subtract this. Go to your calculator, here copy this and paste the same, but here change the inductor to capacitor and try to plot this graph by pressing this button. So this is our new inductor value. So let's try to give M here to mark the graph and D down here to find the difference. Here too we can see the voltage is around 20 volts for our input of 2 volts. So from this we achieved our targeted value. Now let's try to simulate the current magnifier circuit. Here I have rearranged the circuit and changed my resistance value and I have to change the voltage source into current source. So click here voltage source, press Q in your keyboard. Here change the cell name as I sign and give your amplitude as 100M which is 100 milliamps. So click OK, check and save, launch, ADL, choose your analysis as trans, 1M as stop time. Here, in order to find the current, we have to click red dot here. Now run your simulations. So from the simulation, we can see we are giving an 100 milliamps as input. So the input is oscillating from plus 100 milliamps to minus 100 milliamps. And we got our output, which is oscillating from plus 1 amps to minus 1 amps, which is 10 times of our input signal. Now that we have designed our voltage magnifier and current magnifier, we can think of to use them as DC to DC boost converter or amplifier. But can we use them? The answer is no. Because here we are not creating any energy. We are just making it appear big where an amplifier creates power and transfers it. And adding even a simple resistor as the load collapses the total circuit. So as a small experiment for all the Noddies, take a voltage magnifier circuit, add a load resistor and try to decrease the value of the load resistor and observe how the voltage magnification reduced, and you will immediately see the effect of loading on the resonance circuit. So notice, today we learned that resonance can create voltage magnification in series RLC circuit and current magnification in parallel RLC circuit. We saw that both are governed by the same quality factor, but each magnifies a different electrical quantity. And most importantly, we learned that why resonance does not create energy, it simply stores and exchanges it effectively. So that's all for today's video, Noddies. We'll see you in another video. Until then, keep learning, keep simulating, and keep building.